Welcome to Deep Engineering podcast, where we bring you conversations with engineering leaders and architects building real-world systems and shaping the future of modern software.
I'm Saqib Jan, the editor in chief of Deep Engineering and your host.
Today's discussion focuses on how modern software architecture is evolving in the AI-accelerated world, and what engineers need to understand about how to design better, more efficient systems. I'm joined by Jim Ledin, CEO of Ledin Engineering. Jim is an expert in embedded software and hardware design, development, and testing, with deep experience in embedded system, cybersecurity, including assessment and penetration testing. Jim, it's great to have you here today.
Thank you, Saqib. It's great to be here with you as well.
Awesome. Jim, I want to give you the floor. If you could please start by telling us about your background and what led you to focus on computer architecture in the first place.
All right. So my first real exposure to computer architecture was in the 1980s when I had a Commodore 64 computer with its 6502 CPU. I wrote a simple basic program to do some screen drawing, basically moving a dot around the screen with the joystick and pushing the button to draw the lines. And it was slow. It was so slow you could watch it moving one pixel at a time. And that was painful to try to do anything with. So as time went on, I learned a little bit about 6502 assembly language. I found out there are ways that you could actually implement that through the basic interpreter. What you had to do was write out your assembly code by hand, convert it to the opcodes and data bytes, and then poke is the basic command, poke those bytes into memory, and then you could transfer control and execute those. And after I took the inner loops of the drawing program and implemented them in that way, the speed up was amazing. It shot the line across the screen faster than you could see. Episode, I would say, really cemented for me how important it is to understand what's going on in the hardware of a system and not just writing what you want it to do in your favorite language. So my current work, as you mentioned, is focused on embedded systems development and testing, as well as implementing cybersecurity for those systems and doing cyber testing on them. I've done quite a bit of work with electric vehicles, battery-powered systems, the battery management software, as well as the powertrain control systems in those kind of vehicles. Also implementing cyber testing to evaluate what kind of vulnerabilities may be present in systems and trying to exploit those to demonstrate whether or not those actually exist. I've been doing that for about 30 years, over 30 years now, embedded initially, and then later on adding in the cybersecurity aspect. And as kind of a summary, I'd say that the architecture of computer systems is at the boundary where the aspects of performance and system security and behavior in real world situations dealing with all of the unexpected and unusual things that can happen to real systems are happening there. And you really need to understand to make sure across all those domains, security and operational reliability in real world environments, that everything works as expected and intended. You really need an understanding top to bottom, not just what your high level software does, but also at the hardware level, not necessarily saying you need to understand what every instruction's doing, but know how the hardware operates and what kinds of things cause you to run into limits and what kinds of things you can do differently to improve performance, reliability, and security.
Thank you. That you really have an interesting experience. Appreciate for sharing that. And also, you also have a book with us at Packt, which is Modern Computer Architecture and Organization. And also, you now have a third edition of that book. Please tell us more about that, and also maybe what in the field have changed enough to make a new edition necessary rather than just a reprint.
So just to quickly summarize the book, it is intended to start at the beginning. I don't really assume that readers have any background or experience with computer architecture or assembly language instructions or memory cache for pipelines or anything like that. So we really start with history, like where did the first computing devices initially come from? How were they developed? Even starts back in the 1800s when a man named Charles Babbage designed a mechanical computer that was basically intended to be a digital general purpose computing system. It never actually got built, but a lot of the principles that he developed and came up with, including things like pipelining and distributed processing, were implemented in that design. And I thought that was kind of amazing that far back in history, those concepts were being developed. And then it goes through the vacuum tube era in the 1930s, 1940s, the primary systems. And then in the 70s, the Intel 4004 processor, which was really the first microprocessor, and then on to the 8086, 8088, the PC, 8386, which is basically the same architecture, the same base architecture that the modern Intel and AMD-based processors in your PCs and server-based systems use today. So the code running on these modern systems is highly compatible with those systems from decades ago. It's gone from 16 bits to 32 bits to 64 bits, basically adding on capabilities, but not really removing any previous capacity. So the book basically walks through that and then goes into detail of how processors work. First starting with a very simple processor, the 6502 that I mentioned, getting kind of a thorough understanding of that, because all the pieces in that one, the components, the register set, the arithmetic logic unit, the ALU, and the control unit are fundamental components of all processors, essentially all modern digital processors. So we build from there to discuss the modern processors, the latest Intel and AMD processors, the RISC-V processor, basically all the modern systems that are out there, the modern digital processors. The things that have changed substantially since the last version of the book came out was the rise of AI workloads, particularly the altered both for technical developers like ourselves and all of society, what it really means to be talking about an impactful computer architecture. Now moving from the fastest CPU out there to very highly parallelized systems that are optimized to basically perform matrix computations. So the new version of the book, which came out last month in March, has new material that does a deep dive into these new capabilities. There is a chapter that goes in great detail into how GPUs operate, starting at the top level modular structure down to the granular details of processor cores within it. There's another new chapter about transformer-based models, basically looking at them not as somebody who designs them, but more like a mechanic who might want to take them apart and look at them. So we look at all the computations that go on in a particular model, GPT-2, which was one of the earliest and initial large language models that really started to break through as this is something new and important. So we work through what are the calculations that go on that model. And the current frontier models have obviously evolved quite a bit from the days of GPT-2, but they share many of the very same characteristics. So if you can go through GPT-2 and understand how it works, you are a very long way along understanding the latest models. And we are also, as a last point, seeing real diversification of architecture. There were many years where computers, for most applications, were based on the same Intel type architecture, but now across different application areas, you're seeing GPUs, TPUs, tensor processing units, domain-specific accelerators for things like Bitcoin mining computers, local AI in things like cell phones and cars, and the open source RISC-V processor is available to everybody. You can design your own chip based on it. You can implement it in an FPGA. You can do whatever you want, and it's a rapidly growing new, basically, line of processor development. So the book covers all of these topics and has example exercises that walk through a lot of areas to deepen the understanding, including things like implementing a RISC-V processor in a low-cost FPGA like this one. It costs about $99. You can put a RISC-V in that. You can write code, load it, and run it on that. So that's the kind of thing we're trying to get across in the book and the latest version.
Interesting. Thank you, Shim, for sharing experience as well as elaborating the different parts of what you're trying to do.
So GPUs are probably the ideal architecture today for people, small companies that want to run language models locally. I've recently gotten the Gemma 4 26 billion parameter model up and running on an NVIDIA RTX 4090, which, as far as I know, is about the top end of GPUs that you can get today. So for local and personal use, GPUs are the way to go. But for larger scale deployments, where you're running the much larger models, the trend there is for dedicated TPUs. I'm not sure folks are familiar with tensors specifically. A tensor is basically a multi-dimensional array. A matrix is a two-dimensional array. Tensors have more dimensions, and tensors are used widely across AI models. So the work that is going on inside the processing of the models is largely matrix multiplications that are operating on broken down portions of higher dimensional tensors. So a TPU is a processor that's similar in concept to a GPU, but it is very specifically focused on the work of large language model tensor processing. GPUs, as the first letter graphics implies, also have silicon dedicated for generating real-time video and things like gaming and video creation applications. So TPUs do not use up silicon for that purpose. They focus everything on the tensor work, and that's why systems like the NVIDIA Blackwell architecture that is designed for large-scale data center type applications where you're putting a bunch of these components in a rack, interconnecting them with extremely high-speed data links, and they basically work together as a supercomputer. So for larger models, GPUs are not really used. It's more the dedicated hardware that focuses on those. Another factor is that AI workloads are becoming increasingly memory bandwidth limited. That means it's taking more time to bring data into the GPU or TPU memory than it's taking for the computation to take place on the data. So these very high-end systems like Blackwell are being implemented using what's called high bandwidth memory, or HBM. An HBM module is basically a cube that's made of a stack of RAM chips. So they are stacked atop each other, meaning that each one holds a lot of memory, and they're very high bandwidth. On a TPU card, you typically have several of these HBM modules, and they have a far higher data rate for transferring data in and out of the GPU processing components than on a typical consumer grade GPU. And incidentally, this is also why it's becoming hard to find RAM chips like DDR5, because a lot of the production capacity for memory is going into these high bandwidth memory modules, which cost a lot more for the purchaser and make a lot more money for the vendor. So that's basically one of the constraints the rest of us are having to deal with today.
Interesting. Thank you for explaining that. Appreciate the answer. I also want to ask about most software engineers treat the hardware layer as someone else's problem, especially when building in the cloud. So, what does your book argue they are getting wrong by thinking that way? And what does it cost them?
So if you write software and just ignore the hardware limits, that can lead to a lot of hidden costs. If your code is accessing memory in inefficient patterns, if you're not using the cache memory within the processor in an effective manner, and if you're just moving data around more than is necessary, that can all have significant performance impacts. If developers understand how the memory access and caching processes work at the hardware level, they can often tailor code to work more effectively within the constraints and therefore minimize latency. Basically, when the CPU requests data from memory, if it's not available in its cache, it has to wait. You're basically giving downtime when you want to be processing data. A lot of the time it's unavoidable, but the amount of latency can be minimized by different ways of optimizing algorithms. So as an example of this, in a modern PC, each time you read something from DRAM, even if it's just a single byte, 64 bytes are transferred into the CPU cache, and that's what's available at that point for the processor to work with. So for best efficiency, assuming you have options, you would want your code to be working with data from that block before it moves on to something else, rather than kind of bouncing around to other memory locations. Because one thing that would be bad would be if you access several other locations that cause them to be loaded into cache, and then that block that you previously read to be evicted from cache, then you go back and need it again. Now you have to reread it, which is inefficient. Again, it depends on what your algorithm is doing. Only some things are possible, but when possible, you want to basically work through memory in a linear way, and that other things being equal, that gives you the best performance. And if you're working in a cloud environment, not only does that have those issues, but it also results in higher costs, because you are paying for the usage of the system, whether the CPU is actually crunching instructions or the CPU is idle waiting for a data item to come in from memory.
Yeah. Thank you for explaining that. If I am building AI systems today, what are the hardware concepts that would most change how I design them? Something that most engineers probably do not understand well enough. If you could please expound on that.
So data movement, as we've kind of been talking about, can often be more expensive than the actual computation steps. So the latency, especially moving large data structures across different levels of the memory hierarchy, can dominate and leave a lot of your compute bandwidth idle. And this is a concern even with the very highest performance AI focused systems. Getting the memory access capabilities right relative to the processing is a challenge. You definitely do not want to be iterating across large data structures multiple times in an algorithm if there's a way to avoid that. Just talked about going through it linearly is probably going to give the best performance. And then as you do increase parallelization of algorithms across cores and processors, and maybe even across GPUs and other devices, other aspects like synchronization, where tasks on different processors need to sync up, is a constraint. The communication bandwidth between the different processors, whether they're inside the same device or communicating board to board or rack to rack. All of these things affect the efficiency and speed of processing, not just the number of cores you can throw at a parallel algorithm. It's important to understand the costs associated with all of these interactions among parallel activities and optimize around them to get the best overall performance. And then finally, optimizing compilers do a great job of scheduling instruction execution and keeping pipelines full. But there are still things that can be done in code either to make it harder or impossible for them to do that level of optimization. And on the other hand, things you can do that would make it easier and more efficient for them to do what they do. So particularly in performance critical inner loops, minimizing branching can help avoid pipeline stalls because part of what goes on in a modern processor is trying to predict what's going to happen at a branch in your code, basically in an if-else type block. And if sometimes it guesses and it may guess right, which means it's very efficient. It may guess wrong, which means it might have to back up a little bit and start down the path that it didn't take the first time. If you can minimize branching or eliminate it within those most performance critical loops, that makes it easier for the optimizer and the rest of the system to run as efficiently as possible.
Interesting. If you could probably also maybe tell us what's actually happening under the hood in a GPU that makes it effective for AI workload at a level that goes beyond the standard explanation about parallelism.
So as we talked about a little bit, most of the processing in an AI transformer-based model, at least 80% of the execution time is these tensor operations, which are implemented in hardware as matrix multiplications. So the GPUs and TPUs have very specialized multiply and accumulate hardware that is specifically designed to perform these operations. So the current generations of GPUs from NVIDIA at least implement what's called single instruction multiple thread SIMT or SIMT execution, where a group of 32 threads run in lockstep, meaning they're all executing the same instruction but on different data streams, in addition to going along in lockstep. The SIMT capability supports branching, so you can have if-else loops in the code. But again, this has a performance hit. So if you're executing through a stream of data on this SIMT code, and you come to a conditional instruction that some threads take the if part, some threads take the else part. The way the hardware works is it actually executes one side of it, the if part, only on the threads where that instruction triggered flowing through that path. Then it goes back and executes the else part for the other threads. And then at the end of the if-else block, they sync up and resume in lockstep. So this is a trade-off again. So your code can have conditional code in these very lowest level operational sequences on GPUs, but there is the drawback that you basically have an effectively a pipeline stall, or it has to go back and execute a different thread in that kind of a situation. So you have the flexibility, but again, there's a cost. So the NVIDIA processors offer that capability. So again, avoiding branching if possible can have a significant impact on performance. And in general, GPU and TPU performance comes as much from the high memory bandwidth, basically getting data in and out as fast as possible, and latency minimization via effective thread scheduling across the many thousands of cores within a GPU, as well as things like using the SIMT capability effectively. So all of these things, memory bandwidth, minimizing latency, thread scheduling, those all affect the GPU performance in addition to the raw ability to parallelize across the cores. So it's really necessary to manage all of these aspects to get the best performance.
That is helpful. So thank you, Jim. The memory hierarchy from cache to RAM to storage. It's often discussed in theory, but rarely in practice. If you could please explain or maybe give example of where a misunderstanding of memory hierarchy can cause performance problem and what the fix would actually look like.
So I can give one example. There was a web server in some Linux distributions in the early 2000s called Tux, T-U-X, and it was unique in that it ran in kernel. So it avoided a lot of the transfers from user space to kernel space that a web server has to perform during its operation. It only served static pages, and that was because since it was running in kernel, they did not give the pages the processing capability of dynamic paging, dynamic page generation. So one issue with this server was that it had poor cache locality, meaning that the amount of data that it kept active on each request that came in to the web server seemed to be excessive. And so that under a high load, lots of users hitting it at once, the state information grew to exceed the size of the level 2 cache in the CPU, and performance dropped off sharply. So some folks took a look at that and determined that evaluating the cache limitation against the way the code was structured, they could reorganize it so that the amount of data per request would be smaller and therefore be able to remain within the cache limit up to a much larger level of usage. Similarly, that's data caching. Instructions also have a cache in the CPU, and by reorganizing the processing and batching some things, they were able to increase the degree to which instructions would remain in the cache during web server processing, and fixes that they implemented increased the application performance by about 40%. So this was basically examining the behavior of the application in the context of the limitations of the processor hardware and coming up with solutions that respected those limits. And for other applications, similar kinds of fixes might involve restructuring data. For example, you might have a large array of structures that could be more efficiently processed as a structure of arrays in a way that better aligns with the cache limitations, and that might have a big impact on performance. But in these cases, while the design approach is to look at the limits of the system and then try and work within them as best you can, to really understand what's going to have a big impact is you need to implement it and benchmark it in a realistic environment. So that's the kind of approach that seems like it would give the best results.
Thank you for sharing that example, and it's a really useful answer. Appreciate that. There is a growing tension between the abstraction layers that frameworks provide and the hardware costs those abstractions hide. So, at what point does that become a serious engineering problem? And how do you recommend engineers think about where to place that boundary?
So early on in the development cycle, abstractions are great. They're usually a huge win because they can greatly accelerate development and limit mistakes, essentially. Where it becomes dangerous to use too much abstraction is when it obscures what's happening with the data layout in memory and the execution patterns, basically how you're having the processor interact with that data as the algorithm proceeds. And this is especially critical in large scale and real-time systems that have critical performance requirements. So in addition to using abstraction where it makes sense, engineers need to understand what's happening underneath the abstraction in these performance critical applications. And I'm not suggesting to downgrade or not use abstractions. They are entirely appropriate at the level where they preserve meaning and understanding across the team, but they begin to create a problem where they obscure the costs. So it can be most effective to use a two-layer approach. Use the most expressive code at the edges of the system, and in the core, use more performance-aware code. And like I said, it's not necessarily obvious where to make the boundary between a performance-aware code and the more expressive code, but it may take some benchmarking and trials and iterations to, again, identify the best location to make a boundary between those layers.
Thank you. Jim, you also cover architectures in your book for systems like self-driving vehicles. So what makes those architectures fundamentally different from a standard distributed backend system? And what should engineers working in more conventional contexts take from that?
So a self-driving vehicle is both real-time and safety critical. So the software must meet all of its deadlines, basically time limits for producing a response, or else that's not just a glitch or something to blow past. That is a system failure, and that really cannot be tolerated. So in this type of a system, there must be fail-safe responses when unexpected situations occur. And only in the most extreme circumstances, like an unrecoverable hardware failure, would the system be able to refuse to continue processing. Self-driving vehicle tightly couples sensing, computing, and actuating, basically seeing what's around it, deciding what to do, and steering and controlling the vehicle's speed. And that's pretty different from loosely coupled distributed systems. So a distributed system might typically implement retry mechanisms if something fails, and if a system goes down, there are online and offline redundant capabilities that can be brought up, basically switching to a backup if the active system fails. Rather than using this approach, the self-driving vehicles provide a level of redundancy, typically like dual processors that are operating in lockstep. And if one of them experiences a failure, the system continues on the one good one until a repair can be made. This can be extended further. For example, as I understand, the space shuttles, the American space shuttles had 3 computers operating in parallel. And one way that's better than 2 is if you had 2 computers and they gave different answers, you then have to decide which one's good and which one's bad. If you have 3 and 2 of them give one answer and one gives another answer, you probably know the third one is bad. So there's different ways of adding in that level of safety and redundancy. So a way that I think engineers working with more conventional distributed systems can apply these kinds of principles is in situations where the design needs to be fault tolerant and at the same time either minimize or completely eliminate processing interruptions. So that's kind of a different approach. Rather than waiting for a failure to occur, you basically have enough redundant capability in operation simultaneously that you can detect it and basically fix it by bringing up another redundant capability, but you still had other systems keeping it going the whole time. Large systems already operate in that manner, but it may be that systems that don't currently operate that way could operate that way and basically deliver a higher availability level using those techniques.
Interesting. I appreciate how thorough your answers are, and also drawing the insights from your experience. Appreciate that. Jim, for engineers who want to build a real working knowledge of systems and hardware, what is the most direct path in? I mean, not the full curriculum, just the highest leverage starting point?
Well, I would say starting out the way the book starts out, understanding how processors operate at the simplest level of a single instruction. There's 4 steps in an instruction: fetch, decode, execute, and write back. Fetch is when it retrieves the opcode bytes from memory. Decode is when the processor assigns work to the units within the processor, like an ALU for an addition instruction. And then execute is when it actually does the computation or whatever the instruction says to do. And then write back is where it stores the results of that instruction in registers, in memory, and in status bits within the processor. So essentially all processors operate at that very low level, at the level of individual instructions. And then that mental model scales upward to learn about more complex processors and their capabilities. So that's the reason we start in the book with the 6502 processor. It's pretty simple. You can understand what's going on with its registers. It's only got 3 registers. It's 8 bits, so nothing about it is overwhelming in any way. But once you know that, you can build upon that knowledge to get up to the modern processors, which are far more complex, which have hundreds, if not more, instructions available and a lot of very divergent capabilities built within them. It all builds upon these very simple contexts. So the book provides exercises for learning these capabilities and also provides recommendations for where to go to learn more about various topics related to architecture and CPUs and other aspects of digital systems.
Awesome. And looking ahead 5 years from now, what skills will matter most for engineers working, say, at the intersection of software, hardware, and AI?
So I'd say the most important thing is to stay up to date, remain aware of changes as the technology advances. I would say 4 years ago, when the previous version of the book came out, it was not at all clear to me, or I think a lot of people, what was going to be happening with AI in the coming years. So I'd say pay attention to what's going on around you, pay less attention to announcements that may be driven by financial considerations or hype from companies that are focused on their performance in the stock market. Really pay more attention what's actually having an impact in the real world and learn more about them. So in the final chapter of the book, it has a few suggestions for how to go about this, ranging from relying on some trustworthy websites that are really good information about current ongoing activities, both in CPU development and other computer-related activities, as well as more in-depth sources like scientific papers, if you're able and willing to dig in at that level, and even pursuing formal education, which might not necessarily mean going back to college, but it could mean doing things like taking online courses to develop depth in areas where maybe if you're a developer who's got a degree some number of years ago and you want to come up to date, you can do something like a certificate program and update your skills that way. Today, the thing is AI. So developers don't just learn programming languages. You need to be learning about how to interact with AI and use it effectively to develop better software. The way to really understand a system requires the ability to reason across all of the abstraction layers, from the software framework that you're working on at the top level, all the way down to the hardware that runs the code. And again, you don't need to understand or break out the assembly code that's generated by your build tools. But you need to be aware of, even though that's sometimes valuable and can be very helpful, either for learning purposes or to, if you're really in a hot inner loop that needs to be optimized as much as it can go, that's the way to do it. But it's not always or very often about getting to that level. It's more about understanding what the constraints and how the processor works best with things like pipelines and caches, and then orienting your code to work within those environments. And it's also becoming more critical to understand heterogeneous computing environments. So it's not just writing code that runs on a CPU. You might also have code that interacts with the GPU if you're running a parallelized algorithm on that, whether it's a language model or something else. And there's other specialized accelerators that may be implemented within large-scale systems that speed up specific parts of the operation. So there's lots to learn about. It takes a lot of curiosity and searching to get out the best current information.
Yeah, that is edifying advice. Thank you so much. Now that we have come to the end of our discussion, I want to ask one more question. How would you explain the CPU versus GPU distinction to a senior software engineer who probably has never had to care about it before?
Sure. So a CPU is optimized for low latency execution of complex branching code. So I've mentioned how branches can degrade performance in some ways, especially within GPUs, but CPUs are designed to handle that. So although branches do have an impact, they're built to minimize that impact. GPUs work best with highly parallelized and high throughput execution of linear code, or linear to the degree that it can be, operating on these massively parallel workloads. So GPU cores work best when they are going through parallel streams and there's not much branching. And another thing is, if you're developing an algorithm and you're not sure if it should run on a CPU or be split between a CPU and a GPU, the GPU only really becomes attractive when you have enough work for it to do that it can be parallelized and enough that it will amortize the costs associated with moving data onto the GPU, launching the kernels to execute the code, and doing the management work to transfer data to and from the GPU. Because the GPU is really not a computer, if you think of a general purpose computer. It is more of a specialized device that needs to be managed by something else. So you can't really write a program that just runs on a GPU. It needs to be started and managed from a CPU, and you need to get enough benefit from the work that you're doing to get that all brought up and running to make it worthwhile. So if you can't keep the GPU busy with this kind of work, the CPU implementation may win, because it avoids that data transfer and scheduling overhead.
Thank you so much for that explanation. Jim, thank you so much for joining us today and sharing your insights and experiences. It undoubtedly has been a fascinating conversation on how engineers can think more deeply about hardware performance and system design in the AI accelerated world. And to our listeners, thank you for watching this episode of our Deep Engineering podcast. We'll be back with more conversations like this soon. Until the next time. Thank you.
Thank you.